No.
It's the proposition of the accounting company.
And they'll start next week. 2 weeks after next week. All right.
Does everybody know this is a Apple Festival weekend?
Yeah.
Oh, yeah.
No, just.
Just heard. Is there gonna be something in downtown or?
Yeah, that is the festival. I mean, you can, I haven't been to the festival, but it kind of overlaps with birthday,
Oh,
so.
oh, I see.
But it means the freshly harvested apples are available.
Will Tim Cook come?
What?
Will Tim Cook?
You can. Yeah, get corn. Very good. I love our apple. One thing I can confidently say I love about it.
So let's get started. So today we're happy to have Xiaoshuan Wu from the University of Chicago. Xiaoshuan Wu received his PhD from Santa Barbara in 2020. He worked with Schenke. He's currently a Kavanaugh postdoctoral fellow at the University of Chicago. Today he'll tell us about bipartite charge fluctuations and many-body quantum geometry.
Okay, yeah. First of all, can you guys hear me clearly? Just make sure. Okay, yeah. Thanks for the introduction, and I'm really glad. Oh, sorry.
We need to come from the speakers. I mean.
Yeah,
It's the microphone. Oh, speaker, yes.
Echo canceling.
Okay. Press on. What is press on? I don't know. No, I don't think so. That's just a computer.
Yeah, it should be the right thing. It was right last time.
Uh-huh.
Oh. Can you try now?
Can you guys hear me?
Okay.
Okay, good. Yeah. Thank you. Thanks a lot for the introduction, and I'm really glad to be here, especially talking to so many old friends and previous collaborators. So today I will tell you something about bipartite fluctuations and many-body quantum geometry. So this talk will be based on these two papers in collaboration with Prashant Kumar, who just moved from Chicago to IIT in Mumbai at the faculty, and also Kang Cai and Meng Chen from Yale University. In addition, I also want to thank some of my previous collaborators during my PhD, especially there are two related papers. And before I start, I also want to bring your attention to there are two recent papers by from Princeton group and MIT group. They kind of partially overlap with some of our results. Okay. So let me begin with a broad introduction to the background, and no worries if you have never heard of those concepts previously. So the so-called U1 disorder operator is defined like this. Say you have a many-body system with a U1 global symmetry. You can consider the U1 charge inside the subregion, and let's call it A. And you can consider the exponential of the charge inside the region, and this is called the disorder operator, sometimes referred to as full counting statistics. And the so-called bipartite fluctuations are defined like this. So you can view the disorder operator as a generating function, and the second equivalent will give you the so-called fluctuations. And you can see it is ultimately determined by the density-density correlations at equal times. So why this is interesting? In history, there's an experimental proposal for how to measure entanglement entropy, and there are some exact relations between the two concepts. And they have the same scaling behaviors when you rescale the subregion A. They will scale as L log L, and L is the linear size of the subregion. But in general, those two concepts are different, such as in superfluid, the fluctuations with the scale is L log L, but the entanglement entropy to leading order is only L, the boundary of the subregion. And it turns out there are some interesting universal subleading terms in those quantities. Several years ago, there are many papers, including one from us, emphasized the subleading logarithmic contribution if the subregion is not smooth but has a corner. Okay, so this is a local contribution from that singular geometry, the corner contribution. The coefficient here is the current central charge of the CFT, which is universal data associated with the critical point. And then there's a universal angle dependence applies to all the CFTs with U1 symmetry. This analytical result turns out to be quite useful because it can be examined using quantum Monte Carlo simulations, and therefore provide a numerical method to self-consistently verify whether a proposed UV model really corresponds to a unitary CFT. So recent years, people have examined deconfined quantum critical points, I think including both fermionic models and the bosonic lattice models, and their conclusion is the result is not consistent with a unitary CFT. And recently, there's also efforts about checking symmetrical mass generation of Dirac fermions, and they found very promising data consistent with unitary CFT. And in addition, those corner contribution also shows up in entanglement entropies. If you're interested, you could look at these recent papers. And moreover, so that's CFTs. Moreover, in this paper, they also found very interesting results in gapped quantum Hall states. There's also a local corner contribution which does not scale with the system size. So it's a constant piece with the coefficient given by the DC Hall conductivity. And remarkably, they share the same angle dependence. So it is termed super universal angle function in this paper. And more precisely, what they did is that they can derive integer quantum Hall states analytically, and they have verified the results for Lafferty states using wave function based Monte Carlo simulation. Okay. So with those results, certainly you may already have some questions in mind. For example, the first equation, regarding the first equation, can similar universal behavior show up at certain quantum critical points without the conformal symmetry? This type of question may be especially useful for exotic quantum critical points in metals, because other powerful techniques like conformal bootstrap is no longer applicable. However, if such a result can be established, it will be helpful in Monte Carlo simulations to find realizations of interesting field theories. And regarding the second equation, you may wonder, what about compressible states like composite Fermi liquids? They're presumably very different because they're abundant gapless degrees of freedom. And more generally, you may wonder what are the conditions for the second equation? Or what about the anisotropic system, for example? So in order to answer especially the second question, I want to briefly introduce another interesting concept, which is many-body quantum geometry in this context. So I have already mentioned the bipolar fluctuations are determined by the equal time density correlation. I will just use the terminology static structure factor in the following. And by definition, it only relies on the inversion symmetrical part. So you can interchange x and y in a double integral. So you can consider the long wavelength expansion of the structure factor, and the quadratic part, that's generally denoted the coefficient by a tensor GAB. It turns out such a quantity has a very fruitful understanding in history. As you can see, there are so many different names for the exact same quantity. It is the real part of the localization tensor. It is also the polarization fluctuations. And recently, it is called quantum weight by the MIT group. Interestingly, this quantity, the localization tensor, give rise to a general criterion that distinguish charge insulators from ordinary metals by whether this quantity is divergent or finite. This can be understood from the Soles-Wilkins-Martin sum rule, which establishes a fluctuation dissipation theorem type of statement, which relates the localization tensor, which is a ground state property, to the optical longitudinal conductivity. Okay, so which comes from excited states. So in Fermi liquids, you can clearly see that for clean system, the Jude weight will immediately leads to a linear divergence of the localization tensor, which comes from the Dirac function in frequency. And the same results can also be derived using wild identities for the LU1 anomaly, and this can be found in my recent paper. And I also want to emphasize a vanishing Jude weight does not necessarily mean a finite value of the localization tensor. For example, in CFTs, this quantity diverges logarithmically. And most interestingly, in charge insulators, such a quantity is exactly identified as the many-body quantum metric, defined by adiabatic factor insertion or twisted boundary condition. It is defined in the same way as the many-body chain number when people talk about Hall conductivity for fractional quantum Hall states. Okay. Okay, so with this preparation, I can tell you the plan of today's talk. There will be basically two parts. In the first part, I will, for simplicity, only focus on system with continuous rotational symmetry, such that the localization tensor is isotropic. I will talk about two examples. The first one is composite Fermi liquid. According to the localization tensor criterion, this is a compressible charge insulator, okay, broadly defined. And I will talk about critical Fermi surfaces associated with the continuous metal insulator transition in a broad sense, which also includes the composite Fermi liquid to Fermi liquid transition, and also, of course, mode transitions. In the second part, I will address charge insulators with a generic anisotropic quantum metric, the associated universal bonds, and the conditions for their saturation. Okay. So before I proceed, any questions about the introduction, the backgrounds? Okay, so let's look at composite Fermi liquids. I will just use the standard Halperin-Lee-Reed theory to formulate this question at half fini. And under the standard random phase approximation RPA, I can obtain the static structure factor by this Fourier transformation. Okay. And what we found is that in addition to the quadratic part with the coefficient 1/8 pi, there's also a term which is q cube log q. So the q cube log q actually comes from gapless modes. And we have shown that this term only contributes to a boundary loop. There's no corner contribution from this scaling. And similar conclusion has been drawn from the recent paper from Monten's group. And the q square term actually comes from gapped modes, and this will give rise to a subleading corner term, pretty much similar to the gapped corner hole states considered in earlier paper. So if you look at the coefficients, what you really find here is that the bipartite fluctuations actually share the same formula as the gapped corner hole states based on this HLR plus RPA calculation. So the corner term is determined by the hole conductivity. And the leading term is very different from other compressible states like lambda from liquids or superfluids. In those compressible states, you will have L log L, but here is boundary loop. This field theory results has later been numerically verified by this paper using trial wave functions for composite from liquids. They have checked 4 different states for fermions and bosons. And you can clearly see from their data it's pretty linear. So the leading term is the boundary law, and from the intercepts, they can extract the corner contribution, which agrees reasonably with the field theory prediction. Okay. Okay. Then you may wonder, okay, so this is nice, but in general, is it always true for all charge insulators? It turns out it's too good to be true. In general, the quantum metric actually satisfied a topological lower bound by the hole conductivity. So in other words, the result that we have just found is the situation that the bound is actually saturated. I will get back to this later and clarify the conditions for the bound saturation. Okay, so that's composite from liquid. We can also look at the metal insulator transitions. And I emphasize here that those transitions do not have conformal symmetry because you have Fermi surface. There's actually a class of interaction-driven continuous transition share the common theoretical framework, including several recent proposals for marine materials. In the example of mode transitions, one of our previous work is really targeting the experimental observation from Cornell's group. But our focus here is for clean systems. If you are interested in disorder effects, there's a very interesting paper from Dabanjan. I forgot to add the citation here, but yeah. So here we are interested in the clean systems. And I summarize some of the common features of such conditions. So the charge insulators can be either compressible or incompressible. But in terms of the Judah weight, localization tensor, and the charge fluctuations, they have pretty similar behaviors across the transition. And I won't go into the details of the critical theories for each cases, but roughly speaking, this is how they are understood theoretically. So the electron is fractionalized into a bosonic parton and a fermionic parton. Okay, and the fermions is in the mean field states of similar to the original electrons, which is Fermi surface states. And there's a single relevant, presumably single relevant operator in the bosonic sector that will drive this transition. So in the superfluid, in the FL to CFL transition, it is actually in the bosonic parton sector is superfluid to Laughlin states at 1/2. And in the multi-insulator phase, the parton can be either trivially gapped or topological order. Okay, so let me just summarize what we found. For the common features of such transitions from the perspective of localization tensor and charge fluctuations. So we can obtain the structure factor of the electrons from the so-called iPhone locking rule. So basically, there's a gauge invariance requirement here because there will be contributions from the both parton sectors. And what we found is that this localization tensor or quantum metric is actually logarithmic divergent right at the critical point. Okay. And the universal coefficient of this log divergence is related to something called the critical resistivity jump. So the statement is, if you approach the critical point from the Fermi liquid side, the value of the resistivity are not going to be continuous, and there will be a jump in both Hall resistivity and the longitudinal resistivity. And their values are universal data associated with the critical point. And the prediction for the charge fluctuations is that you will have a CFT-like scaling, even if your system no longer have conformal symmetry. Okay. So the point is the nature of those exotic transitions in Moiré materials has not really been confirmed, either experimentally or numerically. So the hope is in future studies, maybe we can use the numerical method based on our analytical results to find potential UV realizations of those universal critical theory. For example, recently, there's actually one microscopic models constructed from those people. They find a bandwidth-tuned CFL to FL transition, which is signaled by the vanishing of the Judah weight. And more precisely, the model is constructed by lambda levels with spatially modulated periodical potentials. So in the future, maybe one can numerically examine the universal behaviors of localization tensor or charge fluctuations to determine whether the transition is continuous or not. Okay, so that's the first part. Just check if any questions for the. Yeah, all right. Okay, so that's isotropic system. What about more generic situation? If there's spatial anisotropy, what will happen? Okay, so previously what I told you is that the corner term only relies on the quantum metric and the corner angle through the very universal angle function. And for anisotropic system, you may naively expect that, of course, it will depend on the corner angle, but it may also depend on the absolute orientation of the entire subsystem, right? And possibly other microscopic details. Okay. Okay. So in this paper, what we managing to show is that based on the continuous or long wavelength models, we can establish a very general harmonic expansion for this corner term. Okay, so the expansion is in terms of the orientation angle phi. We said right here we introduce a capital N to take into account n-fold rotational symmetry, but in general, this is simply a Fourier expansion, so it can always be done for any integer n. So we have found this a class of generalized universal angle functions. And the previously termed super universal angle function is only the zeroth order term. So you can take the limit n to equals to 0, it will reduce back to the previous angle function. And those coefficients C, they are determined by the structure factor as expected, and they are generally non-universal. For example, the first few terms are fully determined by quantum metric, very interestingly, we can use two different ways to extract this this quantum metric information from this corner term. So firstly, you can consider small angle limits. By using the previous mentioned expression of the universal angle function, we can prove that the small angle limit is fully controlled by the quantum metric projected to the normal direction of the cut. And you can also consider the orientation average expression. You can easily see from the harmonic expansion, all the higher order term will vanish, and only the first term remains, which is given by the trace of the quantum metric. So those are the results obtained from the harmonic expansion, and they can be confirmed by an exactly solvable case. So the basic assumption here is that the structure factor only depends on the distance defined by the quantum metric. There will be certain examples from lambda levels I will mention later. But here you only need this generalized rotational invariance. So the trick is that you can use some coordinate transformation to convert the anisotropic system into an isotropic system, and you can do the calculation in that system and considering the transformation of the bipartite fluctuations back to the original system. So we can derive this exact formula for orientation resolved expression. In other words, the harmonic expansion can be summed up exactly in this case. And you can verify both cases, the small angle limits, as well as the orientation average the expression. They confirm the previous predictions. So that is the results from continuous model. You can also look at the lattice models without taking the long wavelength limit. As you expected, as can be expected, the formula will be some discrete formula. Okay. And in order to write something simple, there are some assumptions has to be made. First of all, we assume the lower edge of the subregion is always aligned with primitive vector of the lattice. And for system with unfold rotational symmetry, we always align the origin of the corner to the symmetry axis of the rotations. And based on the formula, is given by the number of bounds. Say you have a separation between the lattice size in B and D, let's call it delta R, is given by the number of bounds times the value of the structure factor evaluated at this value. So it ultimately determined by a procedure of bounds counting. And for commensurate angles, we are able to write down exact formula for the number of bounds. But for other corner angles, there will be a non-universal and it's very non-universal. But for commensurate angles, we can write down the exact formula. So the hope here is that the long wavelength result will be recovered if the subsystem size and the correlation lengths are significantly larger than the lattice constant. So this will reduce to the previous mentioned result for continuous systems. And one can also look at the small angle limits. You can intuitively see the divergence at the small angle because the number of bounds will diverge if you take thermodynamical limits. And one can derive the same results on the lattice, meaning the small angle limit is controlled by the quantum metric projected to the normal direction. And the same lattice results also appeared in a paper from Princeton group. Okay, so I have already told you the important role of the quantum metric in charge fluctuations. But what is the value of the quantum metric, right? What are the allowed values? It turns out in literature, people already understood that there are some bounds for the value. So there's a topological lower bound come from the positive semi-definiteness of the quantum geometrical tensor, okay, which has the quantum metric as its real part and the imaginary part is the Berry curvature. And also there's an energetic upper bound you can understand from SWM sum rule combined with the standard F sum rule. The meaning is that in the insulator, only when the frequency is larger than a gap, it will have a contribution. Then you just replace the frequency in the denominator by the energy gap, and you use the standard F sum rule to derive an upper bound. More precisely, they can be written in this way. So it's a statement about the positive semi-definiteness of these two matrices. And the second one is some explanation. And the delta here is the energy gap of the many-body Hamiltonian. And the DAB here is the diamagnetic response. So basically, it's a double derivative of the Hamiltonian by the background fields A. So the direct implication for the orientation average of the corner term, you can see the coefficient is actually bound in between two quantities. And in the following, I will clarify the conditions for bound saturation in anisotropic lambda levels from two different perspectives. One is Galilean invariance, the other is wave function holomorphicity. Okay, so that's consider the Galilean invariance first. We can think about the problem of lambda levels for non-relativistic particles, and right here we introduce the anisotropic mass tensor, and the anisotropy is captured by a unimodular metric, let's say eta AB, satisfying the determinant equals to 1. So you can easily see that this Hamiltonian has continuous translations and it is invariant on the Galilean boosts, but we no longer have continuous rotations. Okay. Just a quick comment. Previously, I mentioned if the system has generalized rotational invariance, one can derive exact formula for the corner term. This would be a special case of the interaction potential U if the U only depends on the distance defined by the unimodular metric. But in general, it does not necessary to be true. And our central result is the quantum metric is actually fixed by the UV information, the filling factor mu and the shape of the mass tensor eta AB. So it is completely independent of the size of the mass tensor given by the value of the M and the specific form of the interaction potential U. So physically, what happens here is the decoupling of the center of mass degrees of freedom can lead to a generalized cone theorem and can further constrain the density response. we have showed, we have proved the form of the quantum metric based on two approaches. You could consider response theory based on Hamiltonian, or only relies on the word identities for Gaussian boosts and translations. This can be easily established, this result. So if we look at the upper bounds and the lower bounds, the upper bound is actually given, you can see it's given by the derived expression together with another factor, the cyclotron frequency divided by the energy gap. Okay. So for integer quantum Hall states, the upper bound is always saturated. And the lower, for the lower bound, that show for this coefficient of the orientation average of the corner term, it will only saturate when the system is isotropic. And recall, I told you at the very beginning, for composite from liquids, the isotropic version of HLR and the RPA tells you, predicts the quantum geometry, quantum metric is given by the fitting factor divided by 4 pi. You can see it's consistent with the prediction by the Kohn theorem here. And more generally, this normalization of quantum geometry will give rise to non-perturbative constraints on IR field theory. Okay, we have another perspective for the quantum geometry without relying on Hamiltonians. Okay, so it's from the perspective of wave functions. So the starting point here is the system has certain anisotropy associated with intrinsic unimodular metric, eta AB. And in 2 dimensions, there's a complex structure you can define from this metric, and you have complex coordinates as well as the non-level ladder operators defined in this way. And they lead to the center of mass degrees of freedom by summing up all the so the index J here is and then labels the different particles. Okay. So our central results is that's a holomorphicity condition, meaning the ground state wave function is actually annihilated by this center of mass ladder operator, which will fix the quantum metric to be the mu divided by 4 pi times the modular metric. Physically, what this means is the center of mass degree occupies the lowest Noether level and does not mix with higher Noether levels. Okay, so if you look at the many-body wave function, there will be a capital phi times a Gaussian factor, and this capital phi is satisfying the holomorphicity condition with respect to the center of mass coordinate. Okay. So this may remind you similar conditions for the ideal bands and what taxable bands about the holomorphicity, but that's the single particle that's a statement about the single particle band structure. But here it is for the many-body quantum metric, and the coordinate is respect to the center of mass coordinate. Okay, so we can look at some examples where the bound is actually saturated. So I have told you previously there are some quantum Monte Carlo results about charge fluctuations in nothing states and the composite from liquids, and they actually found the saturation of the corner term. So this can be analytically proved here using our criterion. So the Laughlin states, you can easily see the holomorphicity is trivially satisfied. Okay, and as for the composite fermion Fermi-C wave functions, it is also satisfied by using the inversion symmetry. Okay, so those are the starting point of these numerical simulations, and that is why they find the corner term given by the DC Hall conductivity. And of course, there are certainly examples that this bond is actually not saturated. Okay, let's first mention an idealized toy model. Okay, so say you have decoupled number levels, meaning the many-body wave function is a direct product of quantum Hall states at presumably fractional different fitting factors mu n of all the number levels, and you do the anti-symmetrization to get the total many-body wave function. And we can show the quantum metric is given by this formula. You can see that as long as there's some mu n, which is between 0 and 1, it will have some contribution, and meaning and this quantity is not going to be the lower bound. It will be larger than the lower bound. This is, of course, a toy model, but it essentially captures the physics of non-level mixing for the center of mass degrees of freedom. And for lattice models, for example, you could look, you can look at this square lattice Haldane model. Okay, it's very simple, and you can plot the many-body quantum metric and the chain number. You can see that it almost never saturates in a parameter regime. Okay? And more generally, for fractional quantum anomalous Hall states without continuous translations, the topological bounds is generally not expected to be saturated. Okay, so that's pretty much all what I want to tell you, and let me leave the summary here, and I'm happy to take questions if there are any.
Questions for Peter?
Maybe you can explain a little bit more why for fractional quantum Hall the bond is never saturated.
Oh, that's what I mean is anomalous Hall, which means you have a lattice model without magnetic fields, and so you can clearly see from the square lattice Haldane model, you can look at the plot. So the wave function is very different from the lambda levels in Haldane model. So more generally, for lattice models with dispersion, meaning the Berry curvature and the quantum metric is not a constant, it's not homogeneous, that might lead to the violation of, yeah, it's not going to be saturated generally.
Is it the same as vortexability? Like, as if
Oh, that's a statement for single particle bands. Okay, this might be a good question to ask is take those ideal bands and turn interactions to realize certain fractional states and ask what is the value of the many-body quantum metric. I think that has not been explored, has not been understood. So the quantum metric is, this is a many-body version defined by the twisted boundary conditions, and in the ideal bands business, what people talked about is the quantum metric in the Boolean zone in the momentum space. Those are different starting point, but they're related. In a sense, the bounds are understood in the same way by the same indefiniteness of the quantum geometrical tensor.
so can we say that vortexability is a sufficient condition for the bond to be saturated, like for the many-body geometry?
If you stay in a single particle physics without interactions, only take those bands and you evaluate the many-body quantum metric, that will be simply the integration of the single particle quantum metric over the entire Boolean zone. Okay, and you do a trace. So that if the trace and the integral can commute, then of course, yeah, that will lead to a saturation of the many-body quantum metric. But if you turn interactions, then we don't know the answer.
Sorry, maybe this is literally the same question. So you're saying fractional quantum Hall state, even in the presence of ideal band geometry, the answer is not known.
Yeah, it's not.
They're infinitely close to Laughlin states, right? It just
um.
I have a question.
Yeah.
So at some point, I mean, you quoted a lot of results, and I got lost. But at some point you mentioned, structure factor, which is something that's been known for. I mean, people talk about structure factor, even experimentalists talk about structure factor.
Right. Yeah.
The quantity that you're talking about, is it literally structure factor? How is it related to structure factor? And you know,
Yeah.
back in the days of like early days of phenomenal studies, people would do ED and calculate structure factor.
Yeah.
It will be often written as little g, not big G. So what is the relationship between this new name and something that is in the textbook, structure factor?
Oh, okay. Yeah. So, yeah. So, second line is the definition. So, capital G or little g, that's a notation. But basically, the definition is the quadratic part of the textbook defined structure factor. Okay. So this is the localization tensor of polarization fluctuations or quantum weights. This has a long history. Yeah. So the essential message here is that this quantity will show up in the charge.
Structure factor is a charge correlation function. Obviously, it will be sensitive to transitions that involves movement of charge. So that's not surprising, right?
Yeah, that's not surprising at all. Indeed, yeah.
And then what is surprising? I'm trying to figure out what I should remember as a surprise.
Okay, good. So very good. So in literature, there's a long history. This quantity is different in insulators and in metals. It's finite in insulator and it's divergent. It's power law divergent in metals. That's known. Okay. That's well known. The surprising feature, let me see, in which example, maybe in this critical point. Now, the surprising prediction is this quantity is divergent in a very, I would say, strange way, which is logarithmic divergence with respect to the correlation length.
And how do you make that prediction for an interacting system? Is it some RPA result or something?
Good point. So, okay. This is a statement about a class of transitions. There are certain universal field theory description and take those field theory using RPA. Yeah, yes. And we can predict such scaling behavior.
So there are some, you know, wonderful things that you start with and then you do RPA.
That's true. Yeah.
Okay. So how confident should I be on this prediction?
Okay, good. So in those field theory description, so we can look at here. So basically, there are two partons. The field theory is basically saying the fermions are in the Fermi surface states, and the bosonic parton is somehow right at the critical point, which is a CFT. And the statement here for this logarithmic divergence, it really comes from the CFT scaling from the bosonic parton sector. Okay, so there are several issues. You may question whether the CFT is valid. You may also question whether the RPA is valid. Okay, so if the CFT is really a valid starting point, meaning the correlation to the gauge field and the fermionic sector won't change its nature. It's called dynamical decoupled. This hasn't been verified in certain example, but in general, it's not sure. But if this is true, I would be confident about the scaling for structure factor is dominated by CFT sector because the Fermi surface will have a different scaling and CFT always dominate in that case. But indeed, I do not have a very rigorous calculation for the full expression simply because of we do not have a control theory for non-Fermi liquids. But I'm confident the CFT scaling will dominate over the non-Fermi liquid scaling because of the Fermi surface very different from CFT.
Is this something that can be extracted from ED?
I think so. I think so. Yeah, you can change the thickness size. Okay, it depends on which quantity you are talking about. Charge fluctuations, you can change the system size and check the subleading terms. And structure factor, I believe you can just calculate density correlation at equal time.
Well, but you want the coefficient of Q squared piece, which is heavily going to be limited by finite size effects for small system sizes and ED.
Oh, maybe then one could try to see if it is indeed, okay, this correlation length is from how close you are at the criticality, right? So, presumably one can try to see if there's a log behavior by tuning the parameters. Of course, there are many dependencies here, but
Okay, thank you.
yeah.
So if there are no further questions, let's thank the speaker again.
Okay, yeah, thank